Swayam Prabha. Digital India. Educated India.
Hello everyone. In this class, we will first address the question of what kind of finite fields exist, that is finite fields of what size exist, and then we will also try to understand the structure of finite fields. We will see that it is very different from the infinite fields that we are familiar with, like real numbers, complex numbers. So, finite fields of what size or order exist? That is the first question that we will try to understand. So, first of all, let us recall some things that we already know, that is, if we have two finite fields, let us say one is a subfield of the other, k is a subfield of f, both are finite fields. Then what we know is that f is also a vector space over k, and its dimension is denoted by this f colon k, is the dimension of f over k. And then we know that the size of f is size of k power this index of f over k, right. So, if this is m, then size of f is size of k power m. So, this is the first thing we recall, and then let us also recall that the characteristic of a field is defined as the smallest number of 1 that when added gives us 0. Okay. So, if there is no such number, then the characteristic is defined to be 0, and if there is a finite number of 1s which when added gives us 0, then we call that number the characteristic of the field. And we know that the characteristic can be either 0 or a prime number. If it is a non-zero characteristic field, then its characteristic is a prime number. And we also know that if, let us say, f is a field, its characteristic is 0, then the field of rational numbers, we denote it by q, is the prime subfield of f. So, is the prime subfield of f. What is the prime subfield? It is the smallest subfield that the field contains. And if it is a prime number p, then ZP, the modulo p integers, is the prime subfield. Is the prime subfield of f. Now, in the first case, clearly if this is 0 implies that f is infinite field. Because the set of rational numbers is a subset, whereas if the characteristic is a prime number, then it means the ZP is a subfield and then if f is a if f can be a finite field in that case, and then if f is indeed a finite field, then we know that it must be an extension field of Z p, and so it will have a dimension which is finite over Z p. So, f colon Z p is, suppose this number is m, then that means that the size of f is p power m. Okay, there are p power m number of elements, because f is a dimension m vector space over Z p, and then you can express every element of f as a linear combination of a set of m basis elements, and the linear coefficients which are there are of which there are m of them. You can choose them, the coefficients can be chosen each in p possible ways from Z p. So, the number of such linear combinations that we can get is p power m, and hence the number of finite field elements is p power m. So, either a field is infinite field, or if it is a finite field, it has a prime power number of elements. There is a prime number p and there is a positive integer m, such that there are p power m elements in that field. Now, this brings us to the question of whether if we take any prime number p and any positive integer m, is there a finite field of that order or of that size. Okay. The size of the field is also called the order of that field. And this will prove to be true, that this is indeed the case, that is there is a finite field of order p power m for every prime number p and a positive integer m, and those are the only finite fields. For example, there is no finite field of order 6 or 10, etc., which are composite numbers, whereas there are finite fields of order for example 2, 2 square, 2 cube, etc., or 3, 3 square, 3 cube, etc., or next prime number p 5, 5 square, 5 cube, etc., all prime powers, there are finite fields of those orders. Now, this statement we need to prove. So, we know one way to construct a finite field, that is, if we have an irreducible polynomial. Suppose you start with, we want to prove that there is a finite field of order p power m. How do we do that? We take first Z p, which is modulo p integers, and then we take a polynomial f over Z p, that is a polynomial in Z p x of degree m. And then what we know is that we can then take the polynomials modulo f, and that will give us a field of order p power m exactly. So, that is Z p x quotient the ideal generated by f. This is a field, finite field of order p power m. Now, this is if f is irreducible, then this will happen. But as of now, we do not yet know whether such a polynomial exists or not. We have not proved that for every positive integer m and every prime number p, there is an irreducible polynomial of degree m over Z p. So, we cannot take this route to prove the existence of a finite field of order p power m for any prime number p and positive integer m. We will take a different route to prove this. In fact, later we will prove as a consequence that there is an irreducible polynomial of degree m for every positive integer m over Z p. So, okay. So, let us try to prove this. So, first of all, let us note that Sanjay, is this notebook visible? Notebook is not visible, right? Okay. Okay. So, now let us see how to prove the existence of a finite field of order p power m for any prime number p and any integer n. First, we note that if a finite field f has order q, then every element A in f satisfies the following condition: A power q is equal to A. Why is this? This is because, first of all, A, suppose A is non-zero, A is 0, let us take A is 0, then it is obvious A power q is A, because 0 equal to 0. If A is non-zero, then we know that A is an element of the multiplicative group of non-zero elements in F. Any field, its non-zero elements form a multiplicative group that we denote by F star, and the order of this F star, the multiplicative group, this order is q minus 1, right, because F has q elements, you remove the 0 element, there are q minus 1 elements. So, A is an element of a multiplicative group of order q minus 1, and hence A, if you multiply with itself q minus 1 times, that is A power q minus 1 is the identity element of the group, which is 1, and then if you multiply A on both sides again, we get A power q equal to A. So, either when A is 0 or A is non-zero, in both cases we have A power q equal to A. So, this is proved. Now, what does it mean A power q equal to A? What does that mean? It means that A is a root of x power q minus x. Now, x power q minus x can be thought of as a polynomial over Z p. Its coefficients are just 1 and minus 1. So, it is a polynomial in Z p x, and A is a root of that. And so, what is P? P is the characteristic of F. We know that if P is a characteristic of F, Z p is a subfield of F. So, this is a polynomial over Z p, and A is a root of this polynomial. So, now if all the elements of F are thus roots of x power q minus 1. Okay. So, A in F, all A in F is a root, every A. Now, how many such elements are there? Exactly q elements are there. So, there are q roots of x power q minus x that we already have here in the field F. Now, this polynomial is of degree q, and hence it cannot have more than q roots. So, all the roots of this polynomial are exactly the elements of this field F. So, if you take a finite field F, its elements are exactly the roots of the polynomial x power q minus x, where q is the order of that field. Now, this is when a field is already given. Now, if we take any p power m, can we show that there is actually a field with so many elements and they are roots of x power p power m minus 1 minus x? So, this is exactly what we will prove, that if you take this polynomial, take any prime number p and positive integer m, then take this polynomial, there is a splitting field of this polynomial, there is a field where this has all its roots, p power m roots, and we will show that those roots are distinct, and those roots themselves form a field, and hence those roots form a field of p power m elements exactly, and that is exactly the splitting field of this itself. So, this is what we will show. So, let us first write down the statement. This is the theorem. P is a prime number, and let us say m a positive integer, then there exists a finite field of order p power m, and any field of order p power m is isomorphic. Not only that, we will show that by construction we will show that the splitting field of this is in fact a finite field of order p power m, but we will show that any finite field of order p power m is isomorphic to that splitting field. So, it shows uniqueness of any finite field of p power m elements up to isomorphism, isomorphic to the splitting field of x power p power m minus 1. So, let us prove this. Minus x. So, let us take x power p power m minus x, this is a polynomial, and we know that every polynomial has a splitting field. This is a polynomial over Z p. Take its splitting field, suppose f is its splitting field, and so it has all the roots of this polynomial, and suppose S is the set of its roots, that is set of all a in f such that a power p power m minus a is 0. This is the roots of x power p power m minus x. So, how many elements does S have? So, it has at most p power m elements, because all the roots are there, but there may be some repeated roots, and this polynomial cannot have more than p power m roots, because its degree is p power m. So, number of distinct roots can be at most p power m. However, if you take the derivative of this formal derivative of x power p power m minus x is p power m times x power p power m minus 1 minus 1. Now, p power, this is a polynomial over Z p. So, the characteristic p field, and this coefficient is a multiple of p. So, that means it is equal to 0, and so hence this is equal to minus 1. And so, this formal derivative is a constant, and it has no common factor with the polynomial x power p power m minus x. So, this has no common factor with x power p power m minus x. That means that no multiple roots of x power p power m minus x. because if there is a multiple root, we know that it will be also a root of the formal derivative, and this is in fact the formal derivative does not have any root. So, it has this polynomial has no multiple root, all roots are simple, that is all roots are distinct as well. So, there are, so that means S has no root is there 2 times, which means that it has p power m distinct roots. Okay. And S had p power m elements. Now, we will show that S itself is actually a subfield of F. So, we will show that S is a subfield of S is a subfield of F. That is, we will just show that S is a field. So, and this is very easy to verify. 0 is there because elements of S are roots of x power p power m minus 1. So, this is what we have to remember. So, 0 is there, 0 is a root. Okay. So, 0 is in S, 1 is in S, this is obvious, 1 minus 1 here, 1 minus 1 equal to 0. So, 1 is a root. Now, we can check that that if you take it is closed under addition, if alpha and beta are in S, then they are both roots of this polynomial, which means that alpha plus beta is also a root of that. Why? Because this we know that this F is a characteristic P field. So, this is a so this is equal to alpha power p power m plus beta power p power m, and because alpha is a root of this, alpha power p power m is same as alpha and beta power p power m is same as beta, and this shows that this is also a root of x power p power m minus x. So, similarly, one can also show that alpha beta is also in S. So, this is alpha plus beta is in S. Similarly, one can show alpha beta is in S. Inverse is also, if alpha is in S, that implies alpha inverse is in S. This can be shown also quite easily. So, how? For example, alpha inverse power p power m is same as alpha power p power m inverse, but alpha is a root of x power p power m minus x. So, alpha power p power m is same as alpha. So, this is same as alpha inverse. So, clearly alpha inverse is a root of that polynomial. So, it is in S. So, this way one can verify all the required properties of a field, and hence S is a field. So, S is a field. Okay. But S also has all the roots of x power p power m minus 1, and F is supposed to be the so S is a subfield of F, but S has all the roots of x power p power m minus 1, and F is supposed to be the splitting field of F. This is the supposed to be the smallest field containing all the roots, but S also contains all the roots. So, S must be same as F. So, S must be same as F. So, this splitting field has exactly p power m elements, and that proves the existence of a finite field with p power m elements, the first part. Now, this field is indeed the splitting field of x power p power m minus 1. This statement then holds because we have also seen that any field of order p power m is the splitting field is a splitting field of x power p power m minus x, and any two splitting fields of the same polynomial are isomorphic. Hence, all such fields of order p power m are isomorphic and they are all isomorphic to the splitting field of x power p power m minus x. Now, as a consequence of this proof technique, one can also see that if you are given any finite field, not necessarily ZP, what we have done here is that we have started with ZP and then we have extended it, extend to f p power m by taking x power p power m minus x, and we said its splitting field is this. But we can start with any field, let us say f q, where q itself may be a prime power, not necessarily a prime number, but a power of a prime number. And we can take a polynomial over this field, which is x power q power n minus x. Its splitting field will give us f q power n directly. We do not have to go to its prime subfield, because q is a prime power and that prime number is the characteristic of that field as well. So, we do not have to take that prime power, a prime number, and extend that ZP. We can directly extend f q using this polynomial. We can take the splitting field of this polynomial, that will be f q power m. That is it. So, what we have proved is that the for any prime number p and any positive integer m, there is a finite field of order p power m, and these are the exactly all the finite fields that exist. Okay, and those finite fields are obtained as splitting fields of x power p power m minus 1. Okay, now we will study the structure of a finite field, and we will start by understanding what are the subfields a finite field has. So, the result that we will discuss is very simple and clean. It says that if you take any finite field f p power m, this is a subfield of f p power n if and only if m divides n. Now, first of all, note that if the characteristic are different, then one cannot be the subfield of the other, because one has the smallest subfield Z p and the other has smallest subfield another field. So, one cannot be a subfield of the other. So, both the prime numbers p must be the same, but one can be one prime power p power m, another can be another prime power p power n. And so, p power m, f p power m is a subfield of f p power n, under which condition? This is what this theorem is stating, that this is when m divides n. The proof, first of all, note that if f p power m is a subfield of f p power n, then it means that p power n must be a power of p power n, because this is a result that we have seen before. So, this must p power n must be p power m power something, let us call it L, power L, which means that, and this is same as then p power m L, that means n is equal to m L, and that means m divides n. So, this is very simple. If it is a subfield, it must mean that m divides n, otherwise it cannot be a subfield. Now, if m divides n, does it always mean that it is a subfield? So, this is also true, and this can be proved also quite easily. M divides n implies that p power m minus 1 divides p power n minus 1. You can factorize p power n minus 1 easily by writing n equal to m L. One can factorize this with this as a factor. Then this also means that x power this minus 1 divides x power the right hand side minus 1, and then if you multiply x to both sides, it gives us x power p power m minus x divides x power p power n minus x. Just multiplied x on both sides. Now, the roots of these are exactly the finite field, they form the finite field of order p power m. So, the splitting field of this must be a subfield of the splitting field of this. So, f p power m, which is the splitting field of x power p power m minus x, this is a subfield of f p power m. In fact, instead of doing the proof in 2 steps, this part can be removed, and on all these if and all if can be added like this. This can be shown, but it will require a little more work. So, we are not doing it that way. So, for example, if you take the finite field f 2 power 18, what are its subfields? So, f 2 power m, the subfields are of the form f 2 power m, where m divides 18. So, all we need to know is what are the factors of 18. So, first of all, f 2 power 9, because 9 divides 18, f 2 power 6, and then you can take further factors, f 2 power 2, 2 divides 6, f 2 power 3, 3 divides 6 as well as 3 divides 9. So, f 2 power 3 is a subfield of f 2 power 6, and also it is a subfield of f 2 power 9. Now, both these also have subfield f 2, 2 power 1. 1 is a subfield of 1 is a factor of any number. So, f 2 power 1 is a subfield of f 2 power anything. So, this is subfield structure can be drawn this way. So, basically what we are drawing is a parallel version of the factorization, that is 18 has factors 9 and 6, 6 has factor 2, and 3 is a common factor of 6 and 9, and 1 is a common factor of 2 and 3. So, you just write f 2 power 18, f 2 power 9 here and so on, we get this diagram. So, anything that appears below something is with a connection line like this indicates that it is a subfield of the thing above. So, the containment relation of finite fields is the same as the factor relation or divisibility relation for positive integers. Now, the next structural result that we are going to show is extremely important, and it sets finite fields apart from infinite fields, especially 0 characteristic fields that we know of, and that is if you take a finite field f q, then f q star, which is the multiplicative group of all the non-zero elements, this group is a cyclic group. That is, there is a single generator. You can generate all the elements of f q star as powers of one element. That is, there exists alpha in f q star such that f q star can be written as 1 alpha alpha square up to alpha power. F q has q elements. So, f q star has q minus 1 elements. So, the highest power here will be q minus 2, because q minus 1th power will give us 1. So, all the elements of f q star are powers of alpha. So, there is one such element alpha for which all the elements can be written as powers of alpha. This is what this result is saying, FQ star is cyclic. The proof of this, we will use a characterization of cyclic groups that we have done before, and let me repeat that result first. It says that a group G is cyclic. Suppose G has order n, then G is cyclic if and only if, that is, if for every d dividing n, every divisor of n, there is at most one subgroup of G of order d. There are not more than one subgroup of order d in G. If this happens, then G is cyclic. If G is cyclic, then we know that this happens for every divisor d, there is exactly one subgroup, and that is also cyclic. Every subgroup of cyclic group is a cyclic, and its order divides n, of course. And however, for a non-cyclic group, there may be multiple subgroups of the same order. For cyclic groups, that does not happen. So, at most one subgroup of G. In fact, when at most one subgroup of G happens, there will be exactly one subgroup of order d for every d dividing n. So, to prove that a group is cyclic, all we need to do is show that for every factor of n, there is at most one cyclic subgroup of one subgroup of order d. So, let us take FQ star. Suppose so q minus 1 is the order of FQ star. So, take any d dividing q minus 1. Okay. If we take, suppose H is a subgroup of FQ star of order d, then we know that every element in H satisfies the condition that a power d is equal to 1. And how many elements in H are there? There are exactly d elements, because it is a subgroup of order d. So, this means that A is a root of x power d minus 1. So, how many roots are there in H? There are d roots of this polynomial in H, and this is a polynomial of order d. So, there cannot be any other root. On the other hand, let us look at this, think of this multiplicative group. We have identified, suppose there is one subgroup here of order d, d elements are there. There is another cyclic subgroup of order d, which is not the same as this subgroup. Again, d elements are there, which are roots of x power d minus 1. So, in total, if they are distinct subgroups, then in total their union will have more than d elements, and they are all roots of x power d minus 1, and that is a contradiction, because it is a finite field in which there are more than d elements which are roots of x power d minus 1, and that polynomial is of order d, the degree d. So, this is a contradiction if there are multiple cyclic subgroups, multiple subgroups of order d in the multiplicative group. So, that proves that there is at most one subgroup of order d, and then by using this property, this characterization of cyclic groups, it implies that FQ star must be a cyclic group. Now, such elements which generate the whole cyclic group are called primitive elements. primitive elements of a finite field. Okay, these are basically generators of the multiplicative group. Okay, the elements like alpha here that we talked about, alpha is called a primitive element of F q. So, all the powers of alpha and 0 are the elements of that field. All the non-zero elements are powers of alpha. Okay. Next result that we will see, it says that every finite field extension is a simple extension. What is a simple extension? It means it is an extension field that is obtained by adjoining one element. You try to put one element extra in it, and then for that and to make it keep it a field, you need to put a lot more elements, and so finally the field we get, that is called a simple extension. So, every finite field extension is a simple extension. So, if F q is a subfield of, let us say, F r, these are finite fields. And suppose alpha in F r is a primitive element, then F r it can be written as F q with alpha. Alpha is adjoined with F q, then we will get F r. So, basically what this says is that if you have F q, F r is a bigger field, then you have a primitive element, you have taken a primitive element alpha. If you try to put alpha and try to construct a bigger finite field of F q, all its powers, all the powers of alpha must come in. So, there will be nothing left in F r, all the elements will be obtained as powers of alpha, and 0 is already here. So, F r will be the simple extension obtained by adjoining alpha, and that is indeed the proof, that is all. So, if you put alpha, all the powers also must be there in the simple extension obtained by adjoining alpha, and so all the elements of F r will be there. So, F r is equal to that. Okay. So, we will not write down the proof, what I said is just the proof. Okay. Now, we will come to the result that we said we will prove as a consequence instead of starting from there, which is that there is a for every positive integer n and every prime power, there is an irreducible polynomial of degree n over the finite field F q. So, for any F q finite field, where q of course must be a prime power and positive integer n, there exists an irreducible polynomial over F q of degree n. So, to start with, if we had this result already, we could have proved that there is an extension field of order F q power n, order q power n, that is an extension field F q power n. But we have proved that statement separately as a splitting field of x power q power n minus x, and now we want to prove this statement as a consequence. So, first of all we note that Q is a prime power, because F Q is a field, finite field, but then Q power n is also a prime power. Okay. So, that means F Q power n is a finite field. And this field is unique up to isomorphism, and it is an extension field of F Q, because Q power n, Q divides Q power n. So, this is a subfield of F Q power n. Now, we also know that if we take a primitive element of F Q power n, suppose let alpha be a primitive element of F Q power n, then we have just now seen that F Q power n can be seen as F Q extended, so the simple extension of F Q with alpha by obtained by adjoining alpha. And then we know that the minimal polynomial of alpha has degree is the minimal polynomial of alpha over F Q is of course irreducible. We have proved that minimum polynomial is always irreducible. Okay. Alpha is an element from the extension field, its minimal polynomial over F Q is irreducible, and what is its degree? Its degree is exactly the degree of extension that is obtained by adjoining alpha, and is irreducible with degree F Q power n, the index of this, which is n, right. The degree of this extension is n. So, that is it, the minimal polynomial of alpha is exactly such a polynomial. It is an irreducible polynomial over F Q of degree n, and that is what we wanted to prove, that there exists such a polynomial. So, what finally we have proved is that for every finite field F Q and every positive integer n, there is an irreducible polynomial over F Q of degree n. In particular, if we start with, if we take the finite field Z p, whose existence we already knew, then any positive, for any positive integer n, there is an irreducible polynomial of degree n over Z p. And we can use such an irreducible polynomial to extend Z p to get finite fields of any prime power order F p power n. We will get F p power n using such irreducible polynomial by taking Z p x by f, like this. In fact, this is one of the most popular ways of constructing a finite field and using such polynomials to do computations over finite fields and so on. So, finding such irreducible polynomials is of interest, of practical interest as well, for wherever we use finite fields like coding theory, cryptography, everywhere we, whenever we want to construct an extension field, finite field, we use such an irreducible polynomial and then use that to construct the finite field this way, and also use that construction to do all finite field computations. So, how to find such irreducible polynomials in practice is also an interesting problem of interest, and people have studied, and there are methods for computing and coming up with finite coming up with irreducible polynomials over finite fields. Okay, that is all, I think we will stop.